Welcome, everybody. My name is Stephen Holes. I'm the Associate Project Manager for the University Innovation Project, and thank you for joining us today for another ULI Tech Talk. For those who are unaware of what ULI is, NASA's University Leadership Program provides the opportunity for university teams to exercise technical and organizational leadership in proposing unique technical challenges in aeronautics and developing multidisciplinary solutions. Before I hand it off to our PI, just some items for the room. As you might have already seen in the chat, please do not use any AI note-taking or recording services during the meeting. Anyone that joins of that type of software may be removed from the meeting, but you will be able to view the meeting later as it is being recorded by NASA and will be posted through our website where we post the Tech Talks. I'll post the link in the chat. To be put on future invites for ULI Tech Talks, please see the information I will post in the chat. If you have any questions during the presentation, please type them out in the chat. We'll call on your question during the Q&A portion at the end. And with that, I will hand it over to our PI, Naira. Thank you.
Thank you very much for inviting me and giving us this opportunity to share our work of the past 4 years through your platforms. I think I was especially fortunate to have the opportunity to lead this group of outstanding scholars and industry practitioners, guided by our advisory board, to work on these particular challenges that have to do with advanced air mobility vehicles. Our team includes professors from Massachusetts Institute of Technology, Georgia Institute of Technology, North Carolina A&T University, University of Nevada at Reno, with a major number of faculty from University of Illinois at Urbana-Champaign, and our industry partners were Lockheed Martin and Sierra Nevada Corporation. I'm grateful to all of them for their contribution of ideas and their guidance throughout this process. I came to United States back in 1998 to Georgia Tech to work on stability flight control systems. That's when I was first time introduced to aerospace industry. My PhD was in math, and the aerospace industry was presented through these major, powerful, certified technologies that the Georgia Tech group was working on those. As I worked 28 years in this country, the industry faced change to more small-scale, collaborative, human-centered, intelligent solutions that you see on the right. And this transformation of industry happened because the data explosion enabled through CPUs and GPUs that became cheap and available, boosted the machine learning algorithms. We see today large language models, vision language action models that are transforming the way control systems are being designed and deployed. From the perspective of aerospace industry, this transformation can be viewed as going from high altitude to low altitude. By enforcing zero tolerance to accidents, over the 100 years, commercial aviation has reached safety and public trust by flying 4.5 billion passengers per year. The same cannot be said for low-altitude space, which became actively deployed in this century. And the recent DCA airport collision of last year, January, is an evidence of the fact that the low-altitude space still remains largely vulnerable to different uncertainties and unpredictable circumstances. This particular ULI project had one of its objectives to design, deploy safety architectures for autonomous systems that would enable, for example, easy access for emergency response, for healthcare, where we're trying to look into travel time minimization, cargo delivery, and enabling all of this at scale and safely. So the key challenges that we see here of the low altitude space is how to enable operations at scale, given the complexity of these operations, and to ensure that we can achieve it all with safety. That's why autonomy with assured safety may be identified as one of the trusts within NASA ARMD. The technical challenges that this particular ULI has tried to address include safe learning-enabled perception and control, fast data-driven and code-level verification, runtime fault diagnosis and reachability analysis, testing, evaluation, and integration towards technology transfer. We have technical challenge leads present in this 1-hour meeting, and each of them will go into the details of their developments. I will cover the TC1 partially. At the heart of this ULI project is the L1 adaptive control with its 20 years of history. We started the first development in 2004-5, first papers appearing in 2006. During 2007-10, NASA Langley enabled us to fly it on subscale commercial jet that you see here. We were the only controller cleared by the pilots for stall and post-stall flight regimes, enabling data collection at the departure edges of the flight envelope, updating those models. Over the years, we saw increased interest from different industries for commercialization and technology transfer. They were deployed on the evolution autopilots of Raymarine, um, hydraulic pumps of Caterpillar. These are other industries outside aerospace. We had tests on experimental rigs of Statoil and many other developments. Starting 2015, we got the opportunity to flight test it on Learjet and Vista platforms at Edwards Air Force Base. Various challenging scenarios were considered there as saber dance, well known in aerospace industry. And since 2020, we moved into safe learning and control, and we're looking into issues like distributionally robust control, which I will clarify through my talk. Last year, we got already Lockheed Martin putting it on the Vista platform and achieving TRL-6 in a 3G maneuver. As I go ahead, I will clarify now the particulars of the Lockheed Martin flight test. They couldn't join our talk today. Lockheed Martin was funded by also ONR through their SAFE program, and they had the opportunity to augment the L1 adaptive controller on the top of baseline nonlinear dynamic inversion. And with the failed right flap, like hit two guns maneuver, you can see here the performance achieved by L1. Here is a small movie that will show both L1 on and off. They call it safe architecture on and off. The detailed slides of their technology transition can be found on our Aviate website under last year's Autonomy Fest, which happened in University of Nevada of Reno. Some of those movies you will see, but let me turn on this 12-second movie where you will see the left and right for comparison with the safe architecture on and off. You see how L1 handles it pretty well. While without L1, the baseline nonlinear dynamic inversion was not able to keep it in the loop. The results of this paper without the actual flight data have been published in 2025 American Control Conference. You can check the paper, it's available online, and you can see that L1 is referred as the solution for the autonomy architectures as an inner loop controller. We're very thankful for this collaboration, for their leadership, and the paper also highlights some of the future transitions to other Lockheed Martin products. This presentation, as I said, will cover all the TCs. I will start with TC1 and present safe learning-based perception and control. A PhD student of Luisha, Michael, will present the extension of perception simplex to synergetic simplex that incorporates machine learning functionalities into the safety layer. We will have Shayan Mitra covering fast code level verification, and they will show their examples as an intersection between different TCs. We have Ali Karimodini, who will cover the TC3, the runtime fault diagnosis and reachability analysis, and they will show how they incorporate active learning and sensing for discrete faults, which will be an intersection between TC2 and TC3. TC4 is pretty extensive because we have here the flight test validation in industry technology transfers, and we'll have Vasu Salapaka covering network logistics and planning problems in airspace management, where he will present his learning-based parameterized sequential decision-making algorithms, how they scale with the help of AI-assisted tools. Christos Papachristos will show the flight test validations, videos that are very fun to watch. This ULI gave us the opportunities to supervise outstanding PhD students and publish papers in the top conferences and venues that include both machine learning conferences, control conferences, AIAA guidance navigation control conferences, the top journals. Here are some numbers, and these numbers will continue to grow as we're summarizing the results from the last year. Shayan Mitra developed a new course on principles of safe autonomy that gets over 100 students per year who have the opportunity to test some of the algorithms at the Center of Autonomy of UIUC. Our Jessica Patterson from University of Nevada, Reno, who was the flight test engineer on our Learjet flight at Edwards Air Force Base, has actively participated in annual Girls in Aviation by recruiting 30,000 girls in 31 different countries. This is what the Aviation Day, annual Girls in Aviation Day is can be summarized as an event in terms of its enrollment and participation. And Jessica did that actively at University of Nevada, Reno. Personally, I went out here and reached like high school. We have middle school of girls, it's called, in Urbana, and North Carolina had their outreach events. We were very well represented through the drone camp at UIUC and many other events. Now moving to the particular work done within our group. So when we look into autonomy challenges, what we notice, for example, if you're flying a big flight envelope that you see here on the left, you have your flight envelope in front of your eyes that you're tracking, and if there are weather disturbances, you deviate from the flight envelope, you eventually come to land on your flight envelope. When we move into the autonomy world, we see a world where, for example, an emergency response scenario where the autonomous vehicles has to navigate through the disaster area, find its path and redefine it, so there is no predefined flight envelope. I view this as one of the major challenges of autonomy because in this case, the situation changes. We have already kind of vision-based sensors that map the environment. The planner, based on this map, updates the flight envelope instantaneously at every millisecond. And there is a low-level autopilot that has to follow the planner commands. So the challenge is that we see here, what if the autopilot cannot deliver what the planner is asking for? What if the planner does not account for errors in the environmental map? So the autopilot needs to be aware of its capabilities and needs to communicate it to the planner so that they all are in sync. So here is the key challenge. The challenge is that when you have already these vision-based sensors that are generating the map for the planner to produce the instantaneous path, this all happens with data-driven learned components, while our autopilot can be a PID that lives in the deterministic world with Nyquist and Bode defining its gain and phase margins. So the challenge is what should the components communicate if they are born and developed in different worlds, stochastic and deterministic, and what should be the language of communication? These answers are critical for guaranteed robustness and assurance of learned data-driven systems. So the further challenges come with the fact that the guarantees coming from this stochastic world will be sensitive to distribution shifts. We need robustness to epistemic uncertainties, which are the learnable uncertainties, or like the engineers would call known unknowns. We need robustness to aleatoric uncertainties, which are the unlearnable, the unknown unknowns. These are the disturbances and unpredictable environmental uncertainties. And we need also robustness to policy-induced uncertainties, which can be reducible. It's one thing you are dealing with cheap hardware or simulation environments where you can break, fall, get up, learn, collect the data, update the learning algorithm, update the network architecture, and iteratively improve infinitely, like many people do with reinforcement learning, to get acceptable performance level. It's another thing when you're dealing with safety critical systems like airplane or a mission landing on Mars, where the cost is absolutely prohibitive to fly, test, crash million times, collect data, update, re-update, and fly. You just can't kill people infinite times. We need safety architectures where learning is decoupled from the performance. So the autonomy pipeline, as we said, involves the sensors planner system autopilot. The way we have addressed it is the distributionally robust L1 adaptive control. What does it do? So we derived distributional robustness guarantees for the deterministic L1 adaptive controller that was flown on Learjet on the subscale Boeing airplane at NASA and had its guaranteed gain and phase margins. Now we try to understand if these airplanes have flown with L1 adaptive controller that had its guaranteed gain and time delay margins. And this L1 is deployed on a system that's now operating autonomously, where there are vision-based sensors producing the instantaneous updates for the planner. How will L1 work and communicate with this type of new inputs to the system? So we define distributional robustness guarantees for L1. The language is the space of distributions, and we bound in the space of distributions in terms of ambiguity sets the performance of L1 adaptive controller. So these bounds are now derived in terms of Wasserstein ambiguity sets. Let's look what is the stochastic planner doing. The stochastic planner solves a minimization problem over the expectation over an ambiguity set. This ambiguity set is now obtained through the distributional robustness bounds of L1 adaptive controller. As an exercise, we have done it for covariance steering, which is a stochastic planner. Covariance steering now uses the ambiguity set coming from L1 adaptive controller with conditional value at risk constraint for the worst case distribution belongs to that ambiguity set. We get guaranteed margins on state distributions that enable high probability constraint satisfaction. And this is guaranteed over Wasserstein ambiguity sets. There is a tractable formulation by expanding conditional value at risk proportional to this radius of this ambiguity set. Here is a safe navigation of a four-dimensional system, a true system perturbed by unknown nonlinear drift and diffusion. Without DL1, you see the performance on the left where it starts crashing into the obstacles. And with the L1, we can use this safety margin propagated by L1 to find the safe navigation path. The Wasserstein bounds help us tracking distributions in both location and shape. What you see here are the projections of these kind of distributions, and you see that the green eventually tracks the yellow, where the yellow is the nominal, the green is the uncertain. We have also extended it to imitation learning. What do we mean by that? Say, the pilots get trained at first on simulators, and then they go onto the real airplane. And sometimes the pilots, I have heard talking that the simulator was so good that the transition to the real airplane was almost seamless. Nevertheless, there is a difference between the real world and the simulator. And this is where the L1 adaptive controller can help to compensate for the uncertainties. But now as we will move into the autonomy world, and we have the pilot replaced by the autonomous agent, AI agent, we don't want to say, let L1 go and take care of everything. That would be artificially overselling L1. Here, what we see as a potential solution is that you collect pilot's data, you build an imitation learning policy, and you use the imitation learning policy for the AI agent. Now we have two different sources of uncertainty, the model change and the policy change. And within a layered architecture, we can kind of compensate for both with decoupled, guaranteed, provable performance bounds. Here is an example application of that where we show how L1 reduces the imitation learning gap, as you see here. And now we are in the process of testing it on this Guam model provided to us by NASA Langley. Hopefully we will have these results summarized for our May review. We are planning to have a final review of the project on May 4-5. Everyone is invited. It will happen on UIUC campus. The next problem that comes our way, which will already be solved most likely outside this ULI, is the problem of the shared autonomy. What if, for example, the pilot needs to take over the autonomous agent, or the autonomous agent has to take over the pilot? So this is called a problem of shared autonomy, where a game theoretic formulation was ideal to help us to come up with an optimal switch. However, this already goes, as I said, beyond the scope of this ULI. It's like future work, and we are working on it. I'm happy to introduce now Michael Yeriazarian from Louis Shah's group, who will present the work done for perception simplex. And Michael, please take over.
Thank you, Professor Wakiman. I present the work on behalf of our team led by Professors Luisha Boli and Naira Hovakimian. And our focus is ensuring safe perception in autonomous systems within the ULI project. And the National Academy of Sciences take on software safety is very simple. The key to safety is simplicity. And machine learning, which is so abundantly used nowadays, is anything but simple. So our goal is to balance ML performance with safety. That's why Perception Simplex was developed, which guarantees collision avoidance under obstacle detection faults only. And it acts as a safety layer monitoring and overriding ML actions. It addresses a critical failure mode of obstacle detection failure because missed obstacles cause many accidents. And verifiable obstacle detection is the key algorithm that enables Perception Simplex's guarantees. It relies on a simple idea that consecutive LiDAR points with large angle differences indicate an obstacle, as shown on the left figure. This algorithm enables providing a theoretically supported lower bound on obstacle detection, depending on its distance and size, as shown on the right. Well, this is great, but Perception Simplex can be overly conservative sometimes, especially at high speeds, which limits the performance. Well, the safest vehicle is a stationary vehicle, but it's not very useful. That's why Synergistic Simplex was developed, which extends Perception Simplex by incorporating carefully selected machine learning functionality into the safety layer. And it improves performance without losing any original safety guarantees. And I repeat, we do improve performance and we do not lose a single bit of original safety guarantees. And in this way, we get the best of both worlds. We validated synergistic simplex in software-in-the-loop simulations on autonomous ground vehicles, and the results confirmed improved performance with full safety retention. And synergistic simplex as an architecture is likely a strong candidate for future high-performing and verifiably safe systems. Another notable work developed on the ULI is neural probabilistic circuits, led by my colleague Simon Yu, which increases neural network reliability by splitting predictions into semantic components. For example, a heliport is detected by key parts, such as circle, letter H, and white and yellow colors. Another direction of research was SafeLander, led by Professor Boli, and it ensures vehicles follow predefined rules using state-of-the-art models in AI and ML. And it prevents illegal behavior that could compromise system safety. Now, for fast and safe testing of safety-related algorithms, we also developed Air Taxi Sim, a simulator for autonomous aerial vehicles in urban environments based on Carlo. It supports vehicles like Guam and Minihawk, which is the result of collaborations with other ULI teams, such as from the University of Nevada, Reno, MIT, and others. And it provides high-fidelity perception and physics simulation across multiple sensor modalities. And here you see a demonstration of a landing scenario in Air Taxi Sim, showcasing realistic vehicle behavior and environment. Air Taxi Sim supports multiple sensors, such as camera images shown on the left and processed LiDAR shown on the right. And the current state of this work is upgrading from Unreal Engine 4 to Unreal Engine 5, as shown on the next slide, for higher visual fidelity. That's all On my side, I thank you for your attention, and I now hand over to Professor Shayan Mitra.
Shayan, please go ahead.
Yeah, hi. Good morning and good afternoon, everyone. I am Shayan Mitra, and together with Professor Chuchu Fan of MIT, we co-lead the verification certification thrust of this ULI project. Today, I'll be sharing our team's work on verification of urban air mobility, specifically our contributions to certification of multi-agent planning and collision avoidance. Urban air mobility is becoming real. So we can stay on the previous slide, please. And autonomous aircraft are already flying test corridors, as you know. And the hard question, can we guarantee they are safe and won't collide? That does not yet have a satisfying answer. And the certification challenge is very real. The path from tests to approved for urban airspace runs through the area of formal verification. What my colleagues have framed at the system level and dependability level, our thrust attacks at the code level, verifying the actual decision-making algorithms, the neural networks, the dynamics model, as they are written and deployed. As you all know, testing can show presence of failures, but it cannot show their absence. Only formal proofs can. And that is the gap that our work with the VERSE tool is designed to close. Automated reasoning over multi-agent scenarios across nonlinear dynamics, AI decision models to certify correctness and discover risky scenarios before they happen. So let me tell you about the technical challenge as is sketched in this slide. Consider two agents in airspace, each with its own sensor system and its own AI-driven module. Agent I receives sensor readings about Agent J, processes them on board through a neural network. In our case, it's the ACAS-XU network, the airborne collision avoidance system. And based on that processing, it issues advisories to climb up, to steer left or right. The dynamics we are working with comes from NASA Langley's generic urban air mobility model that you heard about earlier. This is a high fidelity reference vehicle model. So we have nonlinear flight dynamics on top of a compressed deep neural network, making real-time decisions. And we need to reason about this whole pipeline together, not just the individual pieces. This is a difficult computational problem and one that existing tools have not been able to handle at scale. So let me introduce the VERSE tool that we have developed in this project. VERSE is a Python library we have built specifically for modeling, verification, and multi-agent scenarios without requiring the users to be verification experts. The core idea driving VERSE is reachability analysis. So instead of asking what happens in this one particular run or test, we ask what are all the possible states that the system could reach given uncertainty in the initial conditions. VERSE propagates that uncertain set forward through the dynamics of the system, through the sensor models and the neural network decision modules. And it uses previous research on sensitivity analysis, tree-based search, and reachability. And recently, we have also integrated it with the CROWN tool for neural network certification. So this lets us make formal statements like under these initial conditions, the aircraft will not lose the required separation. Or conversely, it helps us discover initial conditions that leads to near misses. VERSE has already been used by over 90 students every semester in our autonomy course at Illinois. It's not just a research prototype anymore. It's a working tool which can help with protocol design and analysis. And to our knowledge, this is the first time reachability-based verification has been demonstrated on a hybrid system of this complexity, combining flight dynamics, multi-agent interaction, and deep neural networks. So in this slide, you're seeing a demonstration of the full stack capability of VERSE. We are integrated VERSE with this ACAS-XU neural network, as well as the Guam aircraft dynamics. And you're seeing simulation of two airplanes approaching each other and then avoiding collision in this airspace. shared airspace. The next slide shows a full stack run with 4 aircraft executing ACAS-XU neural network, receiving sensor inputs. We can move on to the next slide. Yeah, thank you. Issuing advisories in real time, and the behavior matches civil aviation conventions. And every run can be replayed and examined so engineers can trace exactly why a particular advisory was issued and where an agent interaction occurred. The next slide shows what the real capability that VERSE brings to the table. This allows formal verification. Here you can see reachability analysis over ranges of initial positions and velocities, not just a single starting condition. And this is where uncertainty in the initial conditions is simultaneously propagated through the sensors, the Guam dynamics, as well as the onboard AI models. This is the key capability that moves us from a few tests to certification. Okay, in the final slide, I'm going to summarize the overall thrust. While we focused on the VERSE tool in today's presentation, which allows us to do verification of urban air mobility protocols via reachability analysis, we have done several other, we have pushed forward several other research directions in this thrust that I did not have a chance to talk about in detail. I'll mention the second radium framework developed by Professor Chu Fan and her group at MIT. This is a method for simultaneous prediction and repair of policies with hardware experiments showing repaired policies that are up to 5 times more robust than their nominal counterparts. And a third method has also been developed at MIT to discover failures arising from sim-to-real gaps that was alluded to earlier by Professor Hovakimian under limitations of hardware budget. So for example, this method shows up to 89 to 100% improvement in prediction of hardware failures compared to much smaller numbers based on simulations alone. So together, these tools form a rigorous and scalable path of certifying autonomous aircraft from code-level verification all the way to real-world robustness. Thank you very much, and I will hand off to Professor Ali Karimuddin next.
Okay, good afternoon. Thank you again. My name is Ali Karimuddin with colleagues Dr. Raptis and Dr. Ornik. We covered the fault diagnosis and reachability analysis. And if we can go to the next slide. Yep, no matter what good practices that we use to design engineering systems, faults cannot be prevented and may happen anytime, anywhere in the system. And at that time, it is very critical to quickly identify what is the source of fault, where it is, and how we can handle it. One example, the flight 191, 1979, it happened, a fault happened, the crew had 15 seconds to recover, but due to the short period of time, they were not able to find to do the root cause analysis and identify the source of fault. And that was one of the factors across multiple factors to contribute to that unfortunate accident. So going to the next slide, motivated by this example, this technical challenge is focusing on how we can identify faults and then come up with recovery plan in the form of reachability analysis that we are talking about in a pretty short period of time, in real time, to speaking that way, right? So now, there are different ways that we have been trying to identify, first of all, the source of fault in a discrete domain and continuous domain. As you see on the picture on the bottom side of the slide, there are two blocks, DES fault diagnosis, the discrete event fault diagnosis, and the continuous fault diagnosis. And then once we detected the fault in these kind of two complementary approaches, we provided that information to reachability analysis unit and then try to come up with recovery plan. And if we go to the next slide, here is the discrete event approach for detecting faults. Having a platform, some of the events are, some of the activities in the systems are discrete by nature, for example, on, off, or sorry, if we can say, and then some of the faults are supposed to be detected from the continuous signals of the system, whether it is a trend, change of a trend in continuous signals of the system, and so on. So collecting all this information, we can come up with a discrete event model of the system, which is very abstract model of the system. Is called automata, for example, right? So having that automata on the middle bottom side of the image that you see, that's a automata for the aileron model of a system that we do have. The actual model will be way larger. And then what we do is developing a diagnoser, which is on the very right side, bottom side of the image, what you see, which is again another automata, which is running concurrently with the system and is trying to narrow down our estimation of the faults in the system. And if you go to the next slide, here is what you see. We have modeled aileron system of and combine it with Guam simulator. The diagnoser is running in real time. We inject a fault around 8 seconds. It's already happened. Now the fault is injected in the form of power failure in one of the actuators. And then now after a few seconds, the system is able to detect faults. So that's what the diagnoser, which I'm referring to, is working. And if you go to the next slide, complementing to this method, my colleague Dr. Baptist and his team have been working on diagnosing fault based on sequential Bayesian filtering method. And what they do is trying to use a sampling-based particle filtering, both the analytical model, and then also they added to make it a little bit more kind of applicable to practical system, which not always the analytical model may be available. So augmenting that whole framework with data-driven models as well. So combining the analytical model plus data-driven techniques, they are trying to identify the probability of fault occurrence. And once the probability reach a certain level, then a fault identification is triggered and then notifying the system. What you see on the video on the right side, an aircraft, a mini-hawk platform, is trying to ascend to a certain altitude. A fault is injected in the form of loss of thrust in one of the rotors. And after a couple of seconds, the probability is reaching to a certain level that we can detect the fault. And knowing that this is particularly very difficult task, especially now the onboard the onboard controller is trying to recover. So there is a fault, the system is trying to recover, yet our fault diagnoser is able to detect the fault and identify the fault. Going to the next slide. So now, having the faults, whether from the continuous, the method that Yanis and Yanis Raptis and my group that is trying to understanding the physical model of the system, as well as the uncertainties that might be involved. Dr. Melkor Orning and his team, they are trying to identify what is the safest reachable set that we can guarantee that we can reach. And because of that, it is pretty conservative because we want to come up with a guaranteed reachable set. And that's pretty difficult if we want to do it over the manifold, over the entire flight envelope. That's very difficult kind of task. So to make it feasible, the method that we have been following is to try to identify, to come up with an adaptive hybridization method over a short period of, or a short horizon that can be computed in real time, so that we can identify the reachable set in real time. So that's pretty much about this thrust, and passing it to the next speaker.
Hello, so I'll be talking about the framework that we're designing, that we are developing for the problems that come in the context of network design, planning, and logistic problems in the context of airspace and air traffic management. So the main the main challenge comes from in these problems come from the fact that they're combinatorial in nature. So the problems that come are like routing, resource allocation, scheduling, congestion avoidance. They have this combinatorial aspect to them, in the sense that the decision space increases exponentially with the number of, for example, say facilities that you may be trying to design. And the current existing literature has essentially algorithms that treat them separately, while in many of our problems they come many of these combinatorial operations are coupled and they come together. So, and if we use the existing generic optimization softwares, they're too slow to be efficient. So what we have done in this work is we have actually identified a class of optimization problems that actually where we exploit a certain common algebraic structure to all these problems. So and the framework that we have developed, which we call as parameterized sequential decision making framework, it allows for multiple such problems, combinatorial optimization problems, to be included in the same formulation, and then we can solve for them. While they are also this framework is flexible enough to include different kinds of constraints, dynamic network dynamics, and then network uncertainties that may be there in the problem. Another nice feature is the sensitivity analysis that that comes as a byproduct of this algorithmic framework. Next slide, please. So over the last year, what we have done is we have taken this algorithmic framework, and then we have used AI and ML tools to make this algorithm scalable. So we have used these tools particularly to emphasize the scalability aspect of it, as well as to learn from the environment, like the uncertainties aspect of it, while keeping the good points that we had from before, that is addressing the combinatorial aspects and coming up with coupled equations. So we are retaining the good aspects and then increasing on the scalability and the uncertainty things. So for example, here we are showing one component that we had from before in the earlier para-SDM framework. There was one component in the algorithm that would become computationally, would explode computationally with the number of facilities. While now with this new, with the AI-enabled algorithm, we can do them the increase is linearly, as shown by the purple line in the left graph. Now, this kind of improvements, previous slide. This kind of improvements has helped us to solve for pretty complicated problems, which I'm showing, for example, on the right, where there's a network design problem where you have the squares to represent a lot of entry points into a network, say by different UAVs, and the stars represent the destinations, and we need to find out the best routes from each square to the corresponding destination star, while also designing simultaneously the facilities along the way. So this is a pretty difficult problem, and with these improvements, we are able to solve it scalably, as well as from our original algorithm, we could get pretty good solutions. Next slide, please. Here's a generic comparison between our algorithms, which I have shown in, which I have highlighted in brown, with respect to earlier existing meta heuristics, and you can see that we are doing almost 10 times better in the obtained cost functions, while also speeding up by at least 2 orders of magnitude to 3 orders of magnitude compared to the existing meta heuristics. So this has made solving these large network design problems possible. And to conclude, next slide. So the papers that I have listed in the previous slide we have shown a lot of details regarding the validation of this framework and how we have made its scalability possible. The main idea here is that we have come with a unified framework that can take multiple combinatorial optimization problems in terms of routing, scheduling, congestion avoidance, collision avoidance, etc. In the same framework, we can solve for these coupled problems while being scalable and accommodating various kinds of constraints. Thank you. So we'll go to the next speaker.
So Christos, please come on with your videos.
My name is Christos Papachristos. I'm an associate professor of the Department of Computer Science and Engineering of UNR. And my talk's about the systems integration, field deployment verification part of this project. I'd like to mention that for this technical challenge 4 component, we work together with Professor Petros Vulgaris, who is the chair of the Mechanical Engineering Department and program director of the Aerospace Program of UNR. Our main goal for TC4 was to provide state-of-the-art aerial robotic systems with an already established high degree of autonomy-related capabilities in perception, navigation, path planning, such that they would be ideal test beds to be flown across the different UAS test sites that we have close to UNR, and to replicate the advanced urban air mobility capabilities set forth by this project, and more particularly its TC1 learning-enabled component products. For this, we developed or further improved upon several pre-existing, previous slide please, upon our several pre-existing UAS prototypes and software architectures in order to facilitate A, diverse embodiments and flight envelopes, B, different scales of aircraft and onboard perception and computation subsystems, allowing to potentially host different flavors and combinations of multimodal sensors, while at the same time C, maintaining a unifying middleware architecture based on the established robot operating system. While some of these capabilities were already established here at UNR or could be incrementally expanded, we also needed compute solutions that are capable of supporting the real-time execution of learning-based algorithms and would fit the UAS robotic architecture and aircraft scale, while additionally thinking forward for how to guarantee safe and repeatable execution of emergency-related test scenarios with our developed platforms. Next slide, please. One such case is the Gannet amphibious UAS prototype that we developed over the duration of our project that is capable of being deployed in water-based environments and survive multiple water surface takeoffs and landings, or even staying immersed over prolonged periods of time. You will notice that this novel platform also has integrated solar-based recharging capabilities such that it can act as a perpetually deployed wide area monitoring system, self-recharging in the wild without needing special infrastructure, while self-hibernating over prolonged periods of time until a critical local event occurs and the vehicle can then sense it, wake up, and rapidly respond by executing a local mission. The vehicle is a VTOL and fixed-wing hybrid and is equipped with a suite of sensors and high-level compute solutions allowing the execution of various navigation routines autonomously. Next slide, please. We name this concept as the new generation of in-the-wild perpetually deployed aerial robotics, but also a critical capability related to this specific system is that we can accomplish a repeat back-to-back testing of autonomous emergency event handling while flying across real-world natural environments with unstructured terrain regions, and more specifically handling of emergency landing while executing non-high altitude flight, pretty much like an urban air mobility platform would. And the safe and repeatable testing characteristic of it comes from the fact that we can even allow the vehicle to choose to land on water, since its amphibious watertight design allows it to survive even staying immersed for a long time. Now, the learning-enabled component that facilitates the autonomy side of things comes from the deployment of a deep learned pixel-level segmentation pipeline that allows classification and segmentation of autonomous regions, of unstructured regions, such as a lake, while an important feature is the fact that the pipeline is actually deployed in real time on the onboard smaller scale compute module that is equipped with a 6-TOPS neural processing unit through a fine symmetric integer quantization of the neural network weights. What you see here is an autonomous execution of such an emergency landing scenario on a local lake. Next slide, please. The cross-architectural approach allowed us to also integrate these capabilities with systems of our industry partner here, Sierra Nevada Corporation, that had recently acquired Valancy, which is a mid-scale hybrid envelope UAS manufacturer, allowing real-world field testing with more powerful payloads and computational capabilities that are closer to what an urban air mobility platform can support. More specifically, the Volley 10 platform that can carry up to 10 pounds of payloads over 50 miles of range, and which was equipped with a multi-camera payload and a powerful NVIDIA Ampere GPU, was also systematically field tested with similar learning-enabled components. Next slide. The goal was to draw experience and data from transitioning to our industry partner capabilities, such as autonomous emergency landing handling at local terrain landmarks that can be identified using visual appearance alone and classified with respect to their admissibility for acting as safe landing zones, offering robustness against possible failure of multiple subsystems, including GPS, due to either fault detecting malfunctions or even to forms of electronic warfare, such as GPS spoofing. Deploying on more powerful GPU architectures comes with the added benefit of increased detection, prediction, and segmentation accuracy of learning-enabled components by avoiding the need for quantization techniques, while also allowing the multi-camera streams to be processed concurrently and smoothly. Next slide, please. Finally, the last field validation testing platform to mention is the Minihawk, which is unique because it is a rapidly prototyped tilt-rotor hybrid, which can be easily reproduced due to its fully 3D printed design, while at the same time it can carry state-of-the-art perception compute modules, including a stereo visual inertial odometry device, a separate USB camera with high focal length optics, as well as traditional autopilot hardware, but also a small-scale compute solution, similar to the one of the amphibious Garnet shown in the beginning, allowing it to use up to 5 TOPS of onboard neural processing unit compute to facilitate the real-time onboard deployment of learning-enabled component capabilities. Yes. I thought somebody wanted to say something. All right. Its rapidly prototyped nature allows both its fast reproduction and possible repair, but also allowed us to share this design with other ULI partners, as previously mentioned. And now UIUC has their own Minihawk to facilitate local real-world testing of autonomy pipelines during early development, which with the added benefits of cross-institution, cross-partner adoption of the same system. Next slide, please. This smaller scale system was ideally positioned to conduct systematic field testing of the trajectory planning framework of covariance steering that grants obstacle avoidance, obstacle collision avoidance with guarantees through sequences of tests conducted at low altitude, but over areas spanning much wider dimensions that any lab indoor location would have. At the stage of field validation, accomplished during our project, such tests included multiple covariance steering-based replanning iterations as simulated obstacles are virtually discovered during a pre-planned inbound landing approach maneuver, resulting in the execution of replanned flight trajectories computed to avoid these virtual obstacles, with safety guarantees based on the covariance steering algorithm developed by a project partner at Georgia Tech, Professor Evangelos Theodorou and his group, and integrated on board the Minihawk platform shown before. Next slide, please. For last, I'd like to highlight that our project organized and hosted an open to the public field demonstration event held here at UNR, which was named the NASA ULI Autonomy Fest. This gave the opportunity to students across all institutions that came to Reno for these days to actively present the products of their corresponding research, not just as presentation slides, but as real-world integrated algorithms and systems working in the field, live, in front of an audience that was formed by both academic and research lab faculty and leaders, but also by industry partners coming from Lockheed Martin, Boeing Aviation, Google Wing, and the Sierra Nevada Corporation. So for the first part of the video here, you can see the execution of the emergency water-based landing live in front of a public crowd, as previously explained. I'd like to mention that this type of autonomous emergency handling situation, by performing opportunistic landing at a local region of the environment based on local information alone and the understanding of mission and aircraft limitations, such as flying too low to reach any non-local infrastructure, is pretty much the same paradigm that we were inspired by in our original proposal for this project, i.e. building a virtual Captain Sally level capabilities into the urban air mobility vehicles of tomorrow, of course, referring to the very well-known and historical decision to emergency land a passenger aircraft on a nearby river, leading to the life-saving so-called Miracle on the Hudson. For the second part of the video, coming up right now, you will see the live demonstration again of replan trajectories computed to provide obstacle avoidance with guarantees based on covariance steering. Let's give it a second. As mentioned, this is again a live demonstration led by students in front of a crowd consisting of industry leaders, but also academic partners. And the platform supporting the execution of this framework is the Minihawk platform. You will note its small size, despite its advanced onboard computational capabilities. And you will note that it is a hybrid VTOL and fixed-wing flight envelope platform, although in this particular scenario, it's mainly flying in VTOL mode. I'd like to mention and highlight the fact that the students that are leading these experiments in the field are a mix that ranges from the PhD level all the way to undergraduate students. And here's the live execution of trajectory replanning in order to guarantee covariance steering-based safe maneuvering approaching a final landing destination. All right, and this concludes my presentation. Thank you very much. And Naira, I will pass the torch to you again.
I want to thank all my collaborators, team members for the time that they took to share the results today, and to everyone who kind of contributed to this project through their ideas, commitment, dedication, advisory board for their guidance, our outreach coordinators who planned high school events, middle school events, and to everyone, to all of you for joining this meeting today. Happy to take any questions if you have.
Thanks, Naira. If anyone has any questions, feel free to put them in the chat or raise your hand. We can call on you. There's a few minutes left for questions. Also, I guess if there's any contact information, you can either display on the screen or put in the chat. So if anyone has questions, that they can reach out to your team.
My apologies for flipping the slides, sometimes not with perfect timing.
All right, Valavani, you have, or Lena, you have the capability to unmute yourself and ask your question. Lena, you have your hand raised. You may ask your question. You're currently on mute. All right. Maybe Milena does not have a question. We are running out of time.
No, I got unmuted, I think. No, you
Go
can hear
ahead.
me. So it's very amazing work that you were able to mesh information theory and AI, machine learning with control theory, which is the discipline that guarantees some things, and optimization. Now, are you able to achieve this by using Verse? Does it work online, or you have some prior setups that you carry on board, and then some modifications happen through L1?
Sharon, will you take that question
Yeah, sure.
regarding Verse?
So Verse is primarily designed to be a offline design
Okay.
time verification tool. We take the models, the controllers, the logic, the dynamics, and we verify whether the system is safe, and we can do that for a bunch of different scenarios. You heard about some of the other techniques
Yes.
from Milkyor's work, which are for online verification as well.
How difficult it is to update for the neural net to get updated in real time? Is that something that's prohibitive, or Can it be done, by your usual segmentation of, partial kind of information?
So updating the decision logic of the airplane while it is flying can be useful for, let's say, if you're training the control algorithm itself, right, in a protected environment. Yeah, so that can be done as long as, many of the frameworks that you heard about are fully differentiable. So you can actually propagate the loss function through the neural network to update it. Verse, again, is for offline verification, not for updating the network.
Thank you very much. Thank you.
All right, thank you for your question. I believe we are running out of time today, so I will put the link to the Aviate Center website in the chat. You can find a lot of the team's contact information there. I want to once again thank you to Naira and your team for an amazing ULI. We're looking forward to your ongoing and following up work in the future. So thank you to everyone for attending another ULI Tech Talk. And I will now stop the recording.
Thank you for having us.
Thank you all. Amazing work.
Thank you.